Calc Review Part 2. In this lesson, I'm going to talk about all the different properties of calculus, starting with curve properties. So if you remember from before, let's say I have x original function, f prime of x, so we're talking about curves. Well, first thing, if it equals 0 or undefined, that's where we find a relative min or relative max. We talked before about the way how you tell if it's relative min or relative max. There's actually two ways. One way is if you do a sign chart. Let's say plus minus plus, I'll give an example. Plus to minus is relative max. Minus to plus is relative min. If anytime you have it where it doesn't change signs, then we call that a stationary inflection. The other way to do is with the second derivative test. We talked about that in the last video. That's where you plug something into the second derivative, and if it's positive, that means it opens up, so it's a min. If it's negative, it means it opens down, so it's a max. Right? But more than that, I want you to understand that first derivative also tells you increasing, decreasing. Right? When first derivative is positive, that's where you're increasing. Your graph's going up, right? The slope is going up, so it's increasing. And if it's negative, you're decreasing. So right here, you'll be increasing from whatever to A, decreasing from A to B, increasing from B to C, and then from C to whatever. So that's what first derivative tells you. First derivative tells you relative min and max. Also tells you where it's increasing, decreasing. The second derivative, when it equals 0 or undefined, is an inflection points. Right, so that's like where it kind of changes from concave up to concave down. It's an inflection point. Now, with this, we also have that we do a sign chart. Oh, sorry, we also have a sign change. So one way it's an inflection point, if the second derivative equals 0, and there's a sign change. So like, let's say this was the second derivative, this would be an inflection point, that would be an inflection point. This one would not, because there's no sign change. Second derivative also tells you when it's positive, it's concave up. Right, so it opens up. And then when it's negative, it's concave down. So it looks like that. Right, so those are like different curve properties. If I want you to figure out where something's increasing, you take the derivative and figure out where it's positive. If I want you to figure out where it's decreasing, take the derivative, figure out it's negative. If I want concave up or concave down, take the second derivative, figure out it's positive or negative. Easiest way to do that is to do a sign chart for either one of them. And if you want to find relative min or max, that's a big one, right? Take the derivative, say equal to 0. If you want to find an inflection point, take the second derivative, set equal to 0, and make sure there's a sign change. Now, with all that in mind, let's look at this problem. So the first step, they want us to take a derivative of this thing right here. Now look at it. It's e to the x times sine of x. That's a product rule. Remember, when we take derivatives, there's rules for this stuff. There's product rules, quotient rule, all that stuff. Integration doesn't have the rules. It's either integrated or u sub. So for this, we're going to do product rule. Our u is e to the x, v is sine x, u is e to the x, v prime, which derivative of sine is cosine. If you're not sure, look at your formula sheet. Plus u prime, derivative of e is this e, times sine x. So that's our derivative. If we want, we can make it a little prettier by factoring out the e, but not necessary. So we have that. Hence, find the exact coordinates of the maximum A. So they want to find a point at maximum A. So again, a couple things going on here. So first, the maximum, you take the derivative set equal to 0. Again, just doing like that, showing that you understand what that means, get a point for that generally. So always write down your thought process. Like, okay, find the max of the derivative equal to 0. So I get set that equal to 0. Sometimes it will require you actually set the equation equal to 0. Then we're going to split it. E to the x equals 0 actually doesn't happen anywhere, so that's no solution. Cosine x plus sine x equals 0. Now this is a little trick. Where does cosine plus sine equals 0? The way I always did this trick was try to get them on opposite sides. And then try to think tan. I know tan is sine over cosine. So I'm going to divide by cosine. I'm going to get. And I get tan of x is equal to negative 1. So I just got to figure out where tan is negative 1 at. All students take calculus, so it's positive here, it's negative here. and here 1 over negative 1, so opposites over adjacent. And then 1, 1 would be a 45-degree angle. So this would be 0 to 180 minus 45 is 135. But really we're probably doing radians here. So in radians that'll be 45 to negative pi over 4. So 4 over 4 and 1 less is 3 pi over 4. Now a little hard to see there, but that's the thought process, right? A little trick review. Set equal to 0. Try to get a little tricky here. I get them on separate sides and I try to put sine over cosine, give me tan. Then I just solve tan. The way I solve tan, the way you solve any trig function, do all students take calculus. It would be in quadrant 2 and quadrant 4 because of tan, and it's negative. And now I did the first one because this is the first max I see, so I took a solve that one, and I got 3 pi over 4. The other one would be 7 pi over 8. So that's the x. I'm not even done, honestly. It said coordinates. I need the y also. I know my x is 3 pi over 4. I still need the y. Now, how do you find the y? Now, notice its coordinates have a. A is on the original graph. You gotta put it into there. So to me, like e to 3 pi over 4 sine of 3 pi over 4. So that's the whole thing. So let it be like that. Might maybe have to use a calculator. Anyway, next up, find the second derivative and simplify it. So right now we have this. I'm gonna go back. We have e to the x cosine x plus sine of x. Right, so they might take the second derivative. It's another product rule. Here's my u, here's my v. Derivative of the first is e to the x times the second left alone. So I'm just gonna do the product rule again. Derivative of the first times the second left alone plus the opposite. Derivative of the second times the first left alone. Now derivative of second, derivative of cosine is negative sine. Derivative of sine is positive cosine. And then e to the x is e to the x. So I get that. I could simplify it because they asked me to simplify it. E to the x cosine x plus e to the x sine x minus e to the x sine x plus e to the x cosine x. These cancel out. These are the same, so I'm going to get 2 e to the x cosine x. So that's it, simplified. Hence, show that a is a maximum. So what this is us doing a second derivative test. They want me to plug a into the second derivative. If I get a positive, then it's a min. If I get a negative, it's a max. So this is all about the second derivative test. So let's plug this into this. Let's plug a, which was this, into the second derivative. So I'm going to get 2 e to 3 pi over 4 cosine of 3 pi over 4. Now cosine 3 pi over 4 is a little trig, right? So 3 pi over 4 is over here. Because this is 4 over 4. 1 less than 3 pi over 4. It is 45, so 1, 1, rad 2. Cosine would be opposite of hypotenuse, so negative rad 2. Negative 1 rad 2 to negative 1. Now I'm going to get negative 2 rad 2 e to 3 pi over 4. This is negative. E is always positive. So that's a negative thing, so it's positive times a negative. Hence, we get a max. So that's how you show it. Again, so just understand what they're asking me, right? Oh, find the max, take the derivative, set equal to 0. Now this is a hard one, which is like trig. Find the second derivative, so take the derivative again. Oh, product rule. Show a is a maximum. That's the second derivative test. I just got to plug my a into my second derivative, and if it's a max, I should get a negative, which is what we did. And then the last one here, it says, find the coordinates of the point B. Well, look at B right here. B is an inflection point. And the way you find your inflection point is to the second derivative equals 0. So let's do that. I already found my second derivative here. 2e to the x cosine x. Set that equal to 0. Split it. 2e to the x equals 0. Again, you can't solve. Natural log of 0 is unsolvable, so that doesn't work. All we gotta do is solve for cosine of x equals 0 at. It's one of these points. This is 1, 0, 0, 1, negative 1, 0, 0, negative 1. Cosine, oof, I didn't mean to cross it out, I meant to highlight it. Cosine is x, sine e. sine is y, so we're looking for cosine is x. So up here, which is pi over 2, and down here, which is 3 pi over 4. 3 pi over 2, sorry. Again, notice how my graph is the first one. It's the first time you see an inflection point. So it's going to be pi over 2. Also notice how this one said the x-coordinate. I don't got to plug it back into my function. I'm just done here. Over here it said find the exact coordinates. So I needed an x and a y. So I was trying to do it before I failed miserably. But that's the general idea, right? The whole point of this is understand that when you take a derivative, this is all like vocab you have to know. You have to know it down straight, right? When you take a derivative, you set equal to 0, that's a min-max. If you just take a derivative, when it's positive, it's increasing. When it's negative, it's decreasing. Second derivative tells you concave up, concave down. Same idea, positive, negative. And then when it equals 0 and there's a sign change, or when you find a sign change, then it's an inflection point, right? It's just vocab. That's all that is. It's understanding vocab. Now let's write the equation of the asymptotes. So let's do a little asymptote review. So there's two types of asymptotes. The vertical asymptote. That's the one you can't cross. It's a vertical line. And the way you find that is always the same, never changes. So the denominator equal to 0. So again, that one never changes. So here's our denominator. So that equal to 0. And you get your vertical asymptote. So x equals 1. Horizontal asymptote. The general idea with that, it's just like, it's the same thing as the limit at infinity. It's your end behavior. Now we do that here is we look at powers. If the top power is bigger than the bottom power, we say none. Also known in this case as positive or negative infinity. If the bottom power is bigger than the top power, then we say y equals 0. And so the bottom two are the ones you see the most often. If the bottom equals the top, it's the ratio. We'll talk about that in a second. So in this case right here, for our horizontal asymptote, we have the bottom power bigger than the top power. This has the power of 1. This has the power of 0. It's like, okay, it's bottom bigger than the top. It should be y equals 0. There's one caveat here. This is 0, but it's plus 2. The whole graph gets moved up 2. So it's actually going to be 0 plus 2. And my horizontal asymptote is y equals 2. The thing with the limit, right? If you're taking the limit at infinity, remember you just plug it in. And then you go up, it's 3 over infinity, which is 0 basically. 0 plus 2 is 2. It's the same idea. Just like doing limits at infinity. So that's a vertical horizontal asymptote. Describe the behavior of f of x equals that for large values of x. That's just a horizontal asymptote. Or, again, the exact same thing, limits as x approaches infinity. General idea here is you want to plug it, basically look at the powers, right? Bottom power bigger than top bigger than bottom, all that good stuff. If the top power is bigger than the bottom power, then it's none or positive negative infinity. If bottom is bigger than the top, it's y equals 0. And if they're the same, like in this case, all you look at is this right here. So 3x squared over 2x squared, look at the ratio. This is y equals. These cancel out, and you just get y equals 3 halves. So 3 halves. So as you get close to very large values of x, your graph gets closer and closer to 3 halves. This is the next one. Given that f double prime of x equals this, so that's the second derivative, and f of x has a minimum at 3, negative 7. So remember, minimum means the derivative equals 0 at 3, negative 7. Find the equation of f of x. So this will take a little bit of work. We want to get f of x. All I have right now is f double prime of x. I got the second derivative. So I got to integrate twice to get back to f of x. So I'll place start. Why wait? And let's just start at the beginning. So we have 2x squared minus 2. Then we're gonna integrate both of these. So if I integrate this side, I'm gonna get f prime of x, right? You go 1 up, just like when we do SVA. Right, we're like down here to go 1 up, so we're gonna integrate. Here you add 1 to the power, divide by a new power. X squared. Here you just add a power. And don't forget, we're integrating, and there's no limit, so plus c. So next, remember, anytime we have a plus c, we want to find it using our point. So we can't use this point yet, because that minimum is on f of x. I have f prime of x. So what point am I going to use? So it gets a little tricky. It's a minimum, so I know the derivative equals 0. So what this says is, hey, when you plug in the x value, because that's where you have a minimum at, that should have been 3, sorry, it equals 0, right? If you have a min at some spot, that means when you plug the x value into the derivative, you should get 0. So that's the point we're going to use to find c. When I plug in 3, it's an equal 0 because right there I have a minimum. And the minimum means the derivative equals 0. So that's the whole idea. We can solve this. And I get 0 equals negative 3 plus c. So c equals 3. So my equation now, don't forget we're just at the equation so far, is this. That's my equation for the first derivative. But now we gotta get this. We gotta get the original function. So we're gonna integrate this again. Let's do it one more time. Now I have f of x. Let's integrate this. Add 1 to the power divided by new power. Integrate this. Negative x squared. Integrate that. Don't forget we don't have no limit, so plus c. Now this time the way I'm gonna find c is do what we did last time. We have a point now. So 3, negative 7. When I plug in 3, I should get negative 7. So negative 7 equals 3 cubed over 3 minus 3 squared plus 3 times 3 plus c. So this is going to be 9. That's going to be 9 plus c. These cancel out. This is 3 cubed is 27. Divided by 3 is 9. It's all 9s. So I get that. So we get negative 7 equals 9 plus c. Subtract 9. C equals negative 16. So now you're like, oh good, great. You're not done yet. Don't forget to write the equation down because that's the question. F of x equals x cubed over 3. Go back to here. Minus x squared plus 3x minus 16. And that's how you find the original equation, right? This never changes. If they give you a derivative and they want you to find the equation above it, they have to give you a point to find your c. In this case, I just had to do it twice. The trickiest thing was the fact that I told you f of x is the minimum. It goes back to vocab. You got to understand what that means. If the min or max, it means the derivative equals 0. That means when you plug your x value in, you should get 0. Just like they said the second derivative equals, just like they said the inflection point, that means the second derivative equals 0. Next problem. Consider the function f of x and g of x equals this. Write an expression for the area. Find the shaded area. Assume that GDC can be used. So we're going to use a calculator for this one. I get it all set up. There you go. Look at that thing. So we have that. They want us to find the shaded area here. So we're going to use a calculator. I don't know why I said it like that. Let's graph this. So on y equals, and then I have f of x, and then I also have x times x minus 3 times x plus minus 5. Now I'm going to graph it. Actually, before I graph, I'm going to change my window. You always want to make the window match the window they have on the problem you're doing. So my y min, I'm going to go negative 10 to 10. Solid. My x min is to go 0 to 10. So there we go. Fix that a little bit. My y min should go negative 10 to 10. So it's all good. Hit graph. That shaded graph looks somewhat like theirs. So I get something like that. Now, again, if I want to find the area of the shaded region, area, first of all, is the integral. That's how you find the area. It's the integral. And the whole idea is we're going to do integral of the top line minus the bottom line. Now, in this case, like you're trying to figure out what the top is, here's the shaded area. What's the graph on top? This case is the curvy one, which is this one. So this is g of x. And then the bottom line is a straight line. So f of x. G of x minus f of x. So this is going to be x minus 3, x minus 5, minus x. All I got to do now is find the limits. We're going to use our calculator for that. Right, so second, calculate intersection, number 5. Just want to get kind of close to where they intersect. So like right there is good. And I get 2.36 makes 2.59. That's what this one is. Remember, you can't just eyeball it. You actually got to use your calculator. So 2.59. And then we got to find the left one. It looks like it's 0, 0, but let me double check. So closer. And it is 0, 0. So 0, 0. Now we're going to put this in our calculator. Now let me show you a trick. If I haven't showed you this already, I think I did, but let's go over it again. So I don't have to rewrite these. If I want to integrate this, I'm going to go quit. I'm going to go to math, f integral number 9. Now 0 to 2.59. Now this, it's top minus bottom, g of x minus f of x. Instead of retyping it all, what I could do is this. I know the bottom one's the top one. Y2 is the top one. That's my g of x. I'm going to get out of this, go here, and I'm going to put alpha trace and go down to y2, which is my g of x. Then put minus alpha trace y1, which is my f of x. Press x. And then instead of having to retype, I just write that, and I get my answer, 11.9. Remember 36 figs for IB. And you get that. Now look at this next one. They want me to repeat the steps for the shaded area below. So, the first part we have down already. That first part is 0 to 1 point something, 2.59 of g minus f. I'll write that. dx. I actually know what that is. That's 11.9. I'm good with that one. What about the next one? Notice how it switches what's on top. Now the top one is the x, and the bottom one is the other equation. So what we're going to do here is we're just going to add on from 2.59 to a value we have to find. It's going to be the other way around. It's going to be f minus g, right? Because now the f one's on top. So we're going to do that. Now, first I got to find the intersection using our calculator. So back to our graph. Second, calculator intersects. Move close to the value. Hit enter a couple of times. Don't hit spacebar like I did, because then you can feel bad like you wasted time for no reason. And you get that, and you get 5.41. And then again, I'm just going to integrate both of these. So let me integrate down real quick. So math, f integral. Now we're going 2.59 to 5.41. I'm using the trick again. I'm going to go alpha trace. Now I know y1's on top. Helps if you click the value. Minus alpha trace y2. By the way, in a little shortcut, how do you know you're doing it correctly? Well, if you get a positive number, right, area in between should always be positive. So 15.1. If you get a negative, that means there's the wrong thing on top. So just fix that, rewrite it, and then you'll be fine. If I add these two up, I'm going to get 27. So that's the area between these two curves. Again, it matters which is on top. So in this case, on top switches. So you got to break up your integral. Integral of that one plus integral of that one. Next up, write the equation of the normal. So writing equation is that y minus y1 equals m x minus x1. Now remember, the normal is a perpendicular one, special. If you want the equation on the tan line, you just do this. Normal is perpendicular, so it means one thing. That means you do the negative reciprocal of the slope. By the way, the slope is the derivative. Remember, you can also say find the equation of the gradient. Remember, that means slope. But normal is special. So gradient is the same thing as slope. Don't forget that. In this case, I want the normal. So look what happened. They gave us the x value already. So this is at 1. If you want to find the y value, you just plug it in. So let me plug that in right now. So it's going to be 1 minus 3 e to the first. So that's going to be negative 2e. So that goes here. Now my m, I'm going to need to take the derivative of this. Now this one's not the nicest one, so let's take the derivative of that. Again, look at it, it's the product rule. Take the derivative of this one times that one, vice versa. U and B. So the first one's just 1 times the second one left alone, plus derivative of the second one, e to the x, so the first one left alone. Now that's my derivative. Don't plug that in for m though. I still got to plug in my x value. So, right, my m here should be a value. So don't just plug that equation. We got to plug in our x value. So it's a derivative at x1. So plug in 1. And these cancels out because that's 0. And I get e. So my m's e. And there's my equation. 1 plus 2e equals e to the x minus 1. Right, so again, equation of a gradient or of a normal. I'm actually a little wrong. This is the equation of the gradient. The normal is perpendicular. I didn't do that. I gotta flip it and change the sign. -1/e. That was embarrassing. Right, so again, equation of a gradient, you just plug it in. Find the y1, find the x1. Slope is always take the derivative and then plug in your x1. Don't just leave the equation, plug in your x1. If it's a normal, then you gotta flip it and change the sign, like I did at the very last second. So now this question says, find the coordinates where the normal cuts f of x again. So that's another way of saying, where do they intersect? Where does this normal equation intersect f of x again? So that's not a good example. So you have this graph here. We have this thing that's a normal, so it's a perpendicular bisector of that. So it's a perpendicular line to it, and it wants to know where does it hit the graph again. So how do we do this? Well, y1, y2. So I was going to graph this. I won't do it here, but on your calc, you just graph it. On the graph, the normal equation we got. And then we'll see where it intersects the equation we just found out. So you move stuff over. -2e, because it's moved to get y by itself. And you just graph it wherever they cross. Use the intersection. Next one, let's do a little displacement, little SVA, kinematics. The velocity function of a particle is given by vt equals this. Meters per second. So again, notice it's a velocity equation. For t greater than 1 second. When t equals 3, the particle is 5 meters right at the origin. So that right there, you gotta keep this in mind, is a point. They're saying the displacement at 3 equals 5. And remember, time is always in the x values, what you plug in. So I'm plugging 3 seconds, I'm at 5 from the origin. Displacement. SVA, right? We're right here. They gave us where it's at. So displacement. So find displacement when t equals 4. So first I gotta find the equation for displacement. We have velocity right now. So I gotta integrate this. Right, don't only go from velocity to displacement, you gotta integrate this. So my displacement, integral of e is this e. This is a t. I can't read my writing. Add 1 to the power, divide by any power. I get t cubed. This is right here is a low reverse chain rule because it's e to a 2t. So remember, the way you integrate that is you copy it, then divide by derivative of the inside. Right? Integration, reverse chain rule. And the integral of 1/t, looking at former sheet, is this natural log of t. And then since we're integrating, there's a limit to plus c. So how are we going to find the c? Well, the point they just gave us. When you plug in 3, it should equal 5. So when I plug in 3, so all this should equal 5. So something to this effect. 6 1/2 plus natural log of 3 plus c. You can use your calculator to find out what c is, some number, then you can rewrite it. My equation is going to be s of t is going to equal t cubed minus 1/2 e to the 2t plus natural log of t plus whatever c happen to be. And then, no, keep in mind they want displacement at 4 seconds. Once I'm done with that, you just plug in 4. So again, the way I did that, I had to integrate my velocity because I want to get to displacement. So I integrate my velocity, and I got this mess. Then it tells me when I plug in 3 equals 5. So I'll plug in 3, set equal to 5. Solve it, probably use the calculator, get some decimal. Don't forget to plug it back in for your c. And once you do that, they want displacement at 4 seconds. So plug in 4. Next question says, find the acceleration when t equals 4. So I got to go down to acceleration. So I got to take a derivative of this thing. So my derivative, let me rewrite v first so it's a little easier. Copy it down. So my derivative of this, well, bring it down, subtract 1 off. So 6t minus. This is an actual chain rule, not a reverse chain rule, because we're taking derivatives. So e to the 2t, copy it, times by derivative on the inside. Like that. You don't divide by x because it's derivative. Now 1/t is probably that has the biggest difference. In integration, you have to know that's natural log. In derivative, we're going to have to rewrite it, t to the -1. Now derivatives, you bring it down, subtract 1 off. So I'm going to get -1 t to the -2. So that's my derivative, and then they want me to plug in 4 seconds. So a of 4 equals 6 times 4 minus e to the 2 times 4 times 2 to 4 minus 4 squared to -2. Again, ugly. Put in your calculator, get an answer. Now, they might ask for the next one down here, right? So now the last thing is actually the newest thing. So this is probably the thing that's the most here. Find the total distances traveled. Now, lucky for us, that's in our formula sheet. If you look at your formula sheet, you can see it says this. It's the integral of v, that's the value of v, dt. So we do exactly what it says. We're going to integrate our velocity equation. Absolute value of our velocity equation. Our velocity equation is up there. That monstrosity. 3t squared minus e to the 2t plus 1 over t absolute value dt. Now, again, it's all about understanding what that means. So, total traveled in the first 5 seconds. So I'm going from 0 to 5. I just put down my calculator, make sure to put absolute value. So if I was doing that on my calculator, just to show you, turn it on. We're going to integrate. So math 9. We're going 0 to 5 because it says the first 5 seconds. And then once I go here, I'm going to go math. I'm going to move over to number. And it has the absolute value sign. So we just plug everything in. Now remember, we don't have t in here, we just use x. We just use x all the time. Minus e to the 2x plus 1 over t. In this case, again, always x. Move over, put dx, and get our answer. Its displacement is taking forever. This is why you use a calculator, because by hand it'll be impossible. And it's still going. Come on. But that's the general idea. Once it gets an answer, I'll let you guys know. And that's going forever. So, the last thing we're talking about today, optimization. So, the steps are, first we're going to draw a nice diagram. And then we're going to separate. So, if you remember we're going to draw a nice diagram to know what we're talking about. And then we're going to set up equations. I like to set two. We put an optimization equation and a constraint equation. So this doesn't have something like, this is going to be like area equals whatever. This doesn't actually have values. You're like, oh, 30 equals 2x plus 2y or something like that. Then what we do is we solve for one of the variables. Usually doesn't matter. So get one of the variables by themselves. And then you plug it into the optimization equation. And then that is what we try to maximize or minimize. How do you maximize or minimize that? Just like the same way we always do. Take the derivative and set equal to 0. You might need to verify if it's actual max or min by doing a second derivative test or a sign chart, but that's the general idea. And actually, that's only one of the main ways you can find the max. Another way you could do it is right here, all the different ways, right? You could verify the second derivative test. You could do a first derivative and do a sign table. Or if you have a calculator and you're like, hey, what's the max of this? What's the max of this equation? You just graph it. And then find the max, right? Using your calculator. So lots of different ways. The easiest way is if it's on a calculator and you just graph it. The mathematical way, if they want you to do it, is you take the derivative, set equal to 0, and then then use a second derivative test to verify to max or min. So let's do a quick example. Anji has decided to create a rectangular pen. She wants the total area of 30 meters squared. Material required for 3 sides costs $4 per meter. The material required for the front side costs $9 per meter. So she wants a 4-sided pen. Now it doesn't matter how we label this. Let's say y and x. Right now, very specific here. She wants a total area of 30 meters. So write an equation of the cost. So we're trying to find the cost of the materials to find the dimension of the minimal cost. We want min costs. Now min cost, what that's going to be the perimeter, because you actually bind perimeter. So min perimeter. So like I said, right, there's always optimization, which in this case is mean our perimeter. Now the way you find the perimeter in this case is going to be, normally it's, let's say, x plus y plus x. There's a little bit of a twist to this one though. The twist is, there's prices. The derivative material costs $4, so we're going to put 4y, 4x, 4y, and one of them costs $9. So my perimeter is going to be, adding all that up, 9 plus 4y plus 4x plus 4y. So 13x plus 8y. Again, a little different because there's costs. So you have to put the cost there too. Area. Right equation for the cost of material. So they want it to be 30 meters squared. So I'm going to get 30 meters squared. Now this has nothing to do with the cost, it's just the length of it. So 30 meters squared is going to equal x times y. So that's our constraint equation. We know that, right, the way we find area is length times width. We know they want the area to be 30 meters. And we know the length is x and the width is y. Again, we're not going to add the cost here because it changes. This is just straight out how do you find the area, x times y. You only put the cost for optimization part. And then what we do, like I said earlier, you get one of these by itself. So let's get, doesn't really matter, let's get x by itself. Divide both sides by y. 30 over y equals x. So I could plug that in over there. So my perimeter is going to be 13. Now instead of x, I'm going to plug in 30 over y plus 8y. So my perimeter is that. Now, if I'm trying to find the minimum cost, again, there's two ways to solve it. One, I could take derivative set equal to 0. If I could use a calculator, then I just plug into my calculator and then figure out what the min is. So I type to my calculator. You notice that there's x's there because remember, we can't use other variables, so just use x. I hit graph and I don't say anything. You probably have to zoom out or fix your window. A couple ways to do it. One way to fix it is zoom fit. Go to zoom, you hit zoom fit. It tries to find a good answer for you. Looks around until I get something to this effect. That's one way. But sometimes, I'm not the biggest fan because sometimes it gives you stuff way off. Look at that. So it's going all the way over there. So that's one way to do it. Other way to do it with by doing mathematics. We'll just try that real quick. So let me rewrite this. This is 0, 390 y plus 8y. So again, I have to take derivatives. Let me rewrite that. 390 y to negative 1 plus 8y. We're going to take derivative set equal to 0 because that's how you find the maximum of anything. So p prime is an equal. Now y to negative 1, so I'm bringing it down, subtract 1 off. So negative 390 y to negative 2 plus 8. Subtract it. Negative 8 equals negative 390 y to negative 2. Just do some mathematics. Negative 8 equals negative 390 over y squared. Cross multiply. Negative 8 y squared equals negative 390. Divide by negative 8. Y squared equals, I'm going to need a calculator for this part. Negative 390, come on, divided by negative 8. And I get about 40.75, and then we're going to square root that. So second, square root answer, about 6.9836. Now that's the y value. It wants the dimensions of minimal cost. So I still got to find the x. That's easy enough. Just plug it back into the equation you have for it. So to find my x, it's going to be 30 over y equals x. So it's going to be 30 over 6.98 equals x. Which means we're going to get 4.30 if you round it to 36. So my dimensions are 4.3 times 6.98. So that's the last of the review videos we have. Funny enough, ouch, that's the sound of an actual mic dropping. So I guess that's my cue to leave.